In this section, we're going to take a look at some applications of systems. What you're going to find in this textbook with the applications is that there's a lot of different options. So I'm going to pick out a couple of applications. Some I'm going to set up and let you solve the rest of them. Others I'll work all the way through. The first of the three main types I want to hit today is finding an equation for a type of function. So if you have 2 points, you can find the equation of a line. Well, if you have 3 points, you can find the equation of a parabola. How do you do that? Well, here's my example. I pre-typed this up here so you don't have to watch me write. Find the quadratic function that contains these 3 points, 1, 4, 2, 1, and 3, 4. The idea is that all of these things are in the polynomial form that looks like this. A little bit different than maybe you're used to seeing, a sub 0 plus a sub 1x plus a sub 2x squared. So normally we write it going from highest to lowest power. In this case, I'm going to write it from 0 power up to the second power. All right, so if the points are 1, 4, 2, 1, and 3, 4, that must mean that there's 3 different equations. When x is 1, p of x is 4. When x is 2, p of x is 1. When x is 3, p of x is 4. So let's start first with the case where x is equal to 1. When x is equal to 1, I get 4 equals a sub 0 plus a sub 1 times 1 plus a sub 2 times 1 squared, which I guess I could write a little bit more neatly as a sub 0 plus a sub 1 plus a sub 2 is equal to 4. All right, let's take a look at the case when x is equal to 2. When x is equal to 2, p of x is equal to 1. So I get 1 equals a sub 0 plus a sub 1 times 2 plus a sub 2 times 2 squared. All right, clean that up a little bit, and I get a sub 0 plus 2a1 plus 4a2 is equal to 1. And then the third case is what happens when x is equal to 3. When x is equal to 3, I get 4 equals a sub 0 plus a sub 1 times 3 plus a sub 2 times 3 squared. So in other words, a sub 0 plus 3a sub 1 plus 9a sub 2 is equal to 4. And so now we can turn this into an augmented matrix and solve it, right? The matrix would look like this. 1, 1, 1, 4, 1, 2, 4, 1, and then 1, 3, 9, 4. In the end, you're going to get 3 values. You go through and reduce this process, you're going to end up with an a sub 0, an a sub 1, and an a sub 2, and then you substitute those values back into the p of x that we had up at the beginning, and you'll get a quadratic. You'll get something to the second power, you'll be able to solve it, and then there's your polynomial. Test it out, make sure the numbers all work. All right, another example that you're going to see in this section are networks. Okay, there's a couple of different examples of networks, but it could be traffic flow, it could be electrical flow. The idea with these networks is that input equals output. So if you think of going around the Somerville circle, the same number of cars that go into the circle should be the same number of cars that leave the circle, but not all exactly the same, right? The same number of cars that leave one highway is not going to be the same as the ones that enter through the other side. But in the end, the same number that go in must go out. So suppose you have some sort of a circle, right? And you've got inputs and you've got outputs. So maybe that x sub 1 will be your input. You'll have an x sub 2 that's also an input. And then you have 50 that go out in that direction. I can say that x sub 1 plus x sub 2 is equal to 50. All the vehicles going into the circle equal the number that are leaving the circle. All right, you can have other versions of this too. You can have more than one variable. You can have more than one that's leaving. So suppose you have, let's say, an intersection here. X sub 2 is going in. 30 cars are going out that way. And then you also have an x sub 1 that's going out. So x sub 2 is going in, x sub 1 and 30 are going out. Sometimes we rearrange these things. If I move the x sub 1 over to the other side, I get negative x sub 1 plus x sub 2 equals 30. Sometimes you want to make that first value positive, so you make it x sub 1 minus x sub 2 equals negative 30. And what that's saying is that there's 30 more cars leaving from X2 than X1, right? The difference between them is 30, with the X2 being bigger because you need 30 more cars to come into the intersection in order to allow the same number to leave that come in. All right, so let's look at a much bigger system that deals with traffic flow. I'm going to snag one from the textbook. If all works out, I should be able to pull it up here so that you could see what it is that I'm doing. So this is from the book. I think it's number 21. There it is. Network analysis problem. All right, so it shows the flow in traffic and vehicles per hour through a network of streets. So you notice that there's 5 roads and 4 nodes, right? Those big circles are nodes. So everything going into each one of those nodes has to equal the amount that's leaving. And so on the top left, right? So if I look at the node that's on the top left, what goes in and what goes out? The X sub 2 and the 400 go in, and the X1 goes out. So if I clean this up a little bit, this gives me X sub 1 minus X sub 2 equals 400. So that's from the node that's on the top left. I have out the one on the bottom left. I've got 4 things that intersect there, 3 that go out and 1 that goes in. Well, that's easy enough. So I get X sub 2, X sub 3, X sub 5 all go out. 300 goes in. So this is the bottom left. Let's look at the top right. On the top right, I've got 1, 2 going in and 2 going out. So X1 and X3 go in, X4 and 600 go out. So when I move that X4 to the other side, I get X sub 1 plus X sub 3 minus X sub 4 is 600. And then on the bottom right side, I've got 2 going in and 1 going out. X4 and X5 go in, 100 goes out. So let's look at the 4 equations that I've got. I got 1, 2, 3, 4. So this is going to be a mighty big system by the time we put this whole thing together. It says solve this traffic system for X sub I equals I, 1, 2, 3, 4, 5. So I want to find out values for each of those X sub I's. And then it gives me certain conditions. Find the traffic flow when one of the values is 0 and the other is 100. Find the traffic flow when they're both equal to 100. And the first thing I need is a matrix. When I set this up, I want to organize this neatly so that I have 5 columns. So the first one says X sub 1 minus X sub 2 is 400. But don't forget, there's 3 other roads. So X sub 3 is 0, X sub 4 is 0, X sub 5 is 0. Number on the other side of the equal sign is 400. All right, for the one on the bottom left, no X sub 1, so put a 0 there. X sub 2, X sub 3, no X sub 4, 1 X sub 5, adds up to 300. For the third one, I have an X sub 1, no X2. I have an X3, negative 1 X4, no X5. That adds up to 600. And then the last one has no 1s, no 2s, no 3s, a 4, and a 5. And it adds up to 100. So that's how I set the system up. Now, at this point, you've got 2 options. If you want a little practice row reducing, you can row reduce. I actually did. It's kind of a fun process. But of course, you make one little mistake and the whole thing goes. The other thing you can do is throw this on a graphing calculator or on some computer program. On your graphing calculator, if you go to matrix and edit, and then designate the size of the matrix you want. So this matrix has 4 rows, right? 4 rows across, and 6 columns. So this is a 4 by 6 matrix. So you would identify it as a 4 by 6 matrix. It'll give you all the blanks. You fill in all the numbers there. And then tell the calculator that you want to do RREF. So I think it's under matrix and edit or matrix and math. And then reduced row echelon form will get you as close to an identity matrix on the left as possible. I'm going to do the old deal where I happen to have the answer in front of me. So I'm going to row reduce this thing on my calculator, and I'm going to get 10101,700 because I think it's more important that I tell you what to do with this rather than just watch me do the calculations. So that'll give me a 300. Right, the third row across has 3 zeros, 2 1s, and 100. But then what happens is you find out the entire last row is all zeros. This is not shocking because what did we have in our original problem? In the original problem, we had 5 rows and only 4 nodes. So we had more variables than we have equations. So if you have more variables than you have equations, you're going to end up with a situation like this that needs a parameter. The other thing is if you row reduce this by hand, how do you know when to stop? Well, what ends up happening is you start flip-flopping back and forth between, let's say, getting rid of a 1 over here, and you move it and it comes up on the top. Then you move it and it comes to the bottom. Then it comes down here. And it keeps flipping back and forth and back and forth. And so after a while, you realize that you're just moving things back and forth and nothing else is going away. All right, so it looks like to solve this problem, I'm going to need some parameters. The whole last row is 0, so let's call my x sub 5 t. All right, so work on the row above it now. If x sub 5 is t, now here's an x sub 4 and an x sub 5. So I've got x sub 4 plus x sub 5 is 100. So it looks like I can write x sub 4 as 100 minus t, right? If x sub 5 is t, I can replace that x sub 5 over there with a t. All right, now when I go to the row above it, I'm stuck because I know what x sub 4 is, but the coefficient here is 0. I know that x sub 5 is t, but I've got these two values over here and no other way to relate them to each other. So what I'm going to have to do is choose a second parameter. In this case, I'm going to choose x sub 3 to be s. So now if I look at that row, x sub 2 plus x sub 3 plus x sub 5 is equal to 300, I can replace x sub 3 with an s, x sub 5 with a t, and now I have a way to evaluate that. Okay, I can represent x sub 2 as 300 minus s minus t. Right, now let's go up to the very top row. The very top row is x sub 1 plus x sub 3 plus x sub 5 is 700. We don't know what x sub 1 is. We know that x sub 3 is s. We know x sub 5 is t. Ah, how convenient. So x sub 1 is 700 minus s minus t. So if you want to organize them all in one place, that's your x1. Your x2 is 300 minus s minus t. Your x sub 3 is s. Your x sub 4 is 100 minus t. And your x sub 5 is t. And you notice that in the textbook problem, they asked you for certain values, and they gave you an x3 and an x5. Well, isn't that funny that that's exactly what the parameters happen to be, right? So you can put in the values that they give you, and you'll get certain results back. But there's more than one answer to this. There's not a fixed number of cars that only works in that condition. There's a lot of different conditions that work. All right, let's try one more example. This one will be based on something that's called Kirchhoff's Law. And it has to do with resistance. So Kirchhoff's law has two parts. You can see in the textbook the whole thing, that the current flowing into a junction has to equal the current flowing out of a junction. So current in equals current out. And the other thing is that if capital I represents the current and capital R represents the resistance, then the sum of all the IRs has to equal the voltage. So if you follow all along the paths, current times resistance plus current times resistance all the way around has to equal the total voltage. That's going to produce a pretty big matrix. So let's take a look. I'm going to pull up another one from the textbook. This one is number 26 in the book if you're following along. It's a system. It's a little bit bigger so you could see. There you go. All right. So all of these little breaks over here, the double bar breaks, those are your voltage supplies. So if it's 9 volts, it could be a 9-volt battery. And then the little squigglies, those are your resistors. All right. So the resistance is measured in ohms. So that's what that little Greek symbol is like that. So if you study physics or something, maybe you know that those are ohms. If not, that's resistance. So the resistance is pushing back. You know, you have resistors in your speakers that you listen to, things like that. So it's pushing back a little bit. So current into a path has to equal the same as the current out. So we're going to get 3 equations based on the current, right? This top box is 1. Then you're going to have a second one over here, and then a third one over here. And then the other thing is that the sum of the IRs is equal to the voltage. So we're going to end up with 6 equations. All right, so on that top block over there, all the current flowing in must equal all the current flowing out. So in that first one, what's flowing in? I3 is flowing in, and I1 is flowing in, so I'm at this guy over here. So at that first one, I3 is going in, I1 is going in, and what's going out? What's going out is I2. Okay, and look at the arrows. They're a little hard to see here, but this arrow is going this way, that arrow is going that way, that arrow is going this way, and that way. All right, this guy's going down like that, and this guy's going up like this. So I've got in, and I've got out. So that's my first equation. All right, look at the one on the right over here. May run out of colors. Let's try this guy over here. All right. So for that one, what's flowing in? I2 is flowing in, and then 1 and 4 is flowing out. So I2 is going in, 1, and 4 is going out. All right, if I come down to the bottom left over here, okay, what's going in, what's going out? The one going out is I3, and the one going in is I5. Oh, there's another one going out. I6 is also going out, right? So this guy's going out down here. I6 is going out. I3 is going out. And I5 is going in. All right. Let's try to make some sense of these 3 equations before we go any further. Over here, I've got I1. I'm going to move the I2 over to the other side. Plus I3 is equal to 0. This second row is I1 minus I2. Well, I'm going to switch this around. So I'll have negative I1 plus I2. So I1 minus I2 plus I4 is equal to 0. And then that third one down there, if I move I5 to the other side, will be I3 minus I5 plus I6 is equal to 0. All right, so those are 3 equations that I've come up with so far for this system. Now, really, there's a fourth one down the bottom right corner over here, and that says that I5 goes out, 4 and 6 goes in. So 4 and 6 goes in, 5 goes out. If I move it over, don't I just get I4 minus I5 plus I6 equals 0? Well, that's the same thing as this line here, except I replace the I3 with an I4. So that's really a duplicate line, so I'm not going to include that again. So all that tells me is that I3 and I4 are the same thing. All right, so those are 3 of my equations. Let's find the other 3. The other 3 come from the sum of all the IRs. And these are actually a little bit easier. So on the top, I've got a resistance of 3 next to the I1. And then on the bottom, I've got a resistance of 2 next to the I2. And the only voltage supply is at 14. All right, work through the one in the middle. That one's got 3 parts. It's got a 2I2. Then it's got a 2 over here times I4. Down the bottom, it's got a 1 times I5. And on the left side, it's got a 4 times I3. All right, how much voltage is in that loop? 25. And then the one down the bottom is a 1 times I5 and a 1 times I6. And the only voltage there is 8. So now I've got 6 equations over here in 6 variables. this is going to make a nice big matrix that I'm not going to solve by hand. So start with the first row, the one that's up in red on the top. Make sure you put zeros anywhere where you don't have a variable. So I've got 1, -1, 1, no I4, no I5, no I6, and a 0 on the other side. The blue line gives me a 1, -1, 0, and then 1, 0, 0, and a 0 on the other side. The green one has nothing in the first, nothing in the second. 1 I3, no I4, -1, 1, and 0. And then now we go down to the 3 lines over here. 3 I1, 2, and then 0, 0, 0, 0, 14. All right, look at the next one. I've got no I1, 2 I2, no I3, 2 I4, 1. Oh, actually, I do have an I3. I have 4 I3s. So what happens when you write them out of order. Okay, so 0, 2, 4, 2. 1 I5, no I6s. And what's on the other side? 25. And then down the bottom, 0, 0, 0, 0, 1, 1, 8. Okay. I am not row reducing that guy by hand. When you put this in your calculator, please double check your entries. 90% of the mistakes people make tend to be they put the wrong number in the calculator. So when you get done with this, reduced row echelon form of whatever matrix you call it will give you a whole bunch of 1s and 0s on the other side. So it'll be 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, all the way down until you end up with a 1 on the end. On the right side, you should end up with a column matrix, 2, 4, 2, 2, 5, 3. Okay, what does this mean? This means that I sub 1 is equal to 2, I sub 2 is equal to 4, all the way down, and these things are measured in amps. So that's how we figure out the current that belongs in each of those places. And notice that at one point we had said we were skipping an equation because I3 and I4 were equal. Look at this. I3 and I4 are both 2 amps. So those are the 3 big things I wanted you to get out of that. How to set up the equation for the parabola, how to set up the networks, input equals output, and then an example with Kirchhoff's law.